Hi there. We're going to be looking now at some periodic variations in the properties of elements. This is one of the great things about the periodic table, that we can use it to help us predict certain properties. It won't always exactly get it right, but it'll get the general trend. The three trends we're going to look at, as you see in the objective here, is atomic size or atomic radius, ionization energy, and electron affinity. So we're also going to learn about those properties as we go along. The periodic table, when the periodic table was originally created, it wasn't created, people didn't know about really protons, neutrons, or electrons or anything like that, even though we just went through a lot of work where we were relating the electronic configuration of the periodic table, the electron configuration of the elements to the periodic table. The periodic table was actually put together initially to try and organize elements by their properties, and the fact that we then later on were able to come up with an underlying reason for why it's arranged that way and why the properties behave that way is kind of cool. So again, we're going to look at these three properties: size, or radius, ionization energy, and electron affinity. There are other ones that you'll learn later on, but we're just going to focus on these three for right now. All right, so the radius of an atom, if you think about an atom as kind of a sphere, and we're going to quickly run into the limits of my artistic ability. I think we hit it right about there. If the center is there, right there where that dot is, no matter where you measure out to the edge, that's going to be the radius of the atom. Now, it's really kind of hard to measure the radius of an atom. What this sentence up here talks about is that if I have two atoms that are joined by a covalent bond, and I can tell that the nuclei, which I'm indicated by the parts, are that far apart, then that distance d is going to be equal to 2 times the radius. It's going to be one radius here, one radius there. So that's what that simply says. That's the way we can measure the radius. It gives us kind of a guide to that. Now, the big underlying concept here is something called the effective nuclear charge. Z normally stands for the nuclear charge. That's the atomic number, or the number of protons. The effective nuclear charge, Z sub EFF, sometimes you'll see that written as Z star as well, basically says, okay, if we're thinking about what the outermost electron sees, what it feels, what it senses from the nucleus, we have to take into account not only the protons that are in the nucleus. So here I'm going to draw lithium nucleus with some protons, and if we think about the energy level, first energy level being there, and the third energy level being out here, what happens is that our outermost electron here that I'm drawing in yellow, okay, what it sees if it looks back is it sees these 3 protons here, but it also sees some amount of screening from those 2 electrons that I just shaded in blue. So the effective nuclear charge in this case is going to be equal to the nuclear charge minus some shielding factor, and that factor is going to be proportional to the number of inner electrons, core electrons. It's going to be, some factor, and we could get into more detailed things about trying to predict what that is, but again, that's really far beyond this course, or even beyond the course you'll be taking for the next 2 years, general chemistry course. But let's just compare, though. Let's look at the next one. So this is lithium, right? The next element is beryllium. So beryllium's got 4 protons in its nucleus, and it's got an inner core of 2 electrons, just like we said. And on the outer electrons, we've got 2 out there as well. So now, if we're thinking about this outermost electron here, oops, change the colors around, he sees the four blue protons, and then is shielded now in yellow by these inner ones. But this other electron out here, it doesn't do much shielding because it's not in between the outermost electron and the core. So if we had just a simple shielding factor, if we said that they were perfectly shielded, that the factor was 1, this Z effective here would be 3 minus 2, or 1. This Z effective would be 4 minus 2, or 2. So the Z effective goes up as we go across the periodic table. And again, it's not that effective. My example is an extreme level of effectiveness, but the trend basically is that as you go across the periodic table that way, Z effective goes up, which means the electrons are experiencing stronger attraction back to the nucleus. Okay. So if we think about going across a period, remember on a periodic table, going across is called a period. Going down is called a group or a family. If we go across a period, the higher effective nuclear charge pulls those electrons in. So what happens is, as I go across this way, my radius decreases in that same row. Now obviously, if I'm going up, the radius is also going to decrease because we have much smaller atoms with much less electrons as you go up one row. You're typically going down by 18 or 8 electrons, or depending on where you are. So the radius decreases in that way. Usually what we would say is we draw it this way and say that the radius increases as we go left and down on the periodic table. That would be a summary of the trend. And again, this is due to the effective nuclear charge. This is due to the number of electrons and having going into principal energy levels that are 1 higher as we go down the periodic table. Here are some data about this and some images about how big things are. And I just want to clarify, if you're ever asked on a question or an exam or anything to make a prediction of one of these periodic trends, you're not being asked to look them up from some resource and figure out what they are. What you're being asked is to use the concept of the trend in the periodic table to make a prediction. That's a different thing. So be sure you understand that. Here's another representation of it. This is a graph by atomic number, or Z, and then we have the actual radius. That radius is in picometers. A picometer is 10 to the negative 12th meter, right? So PM is 10 to the negative 12th meters, so very, very small distances. And you see what happens is that as you go across a row, say from lithium to neon, that generally the radius goes down, and then when we jump up to the next row, it goes up quite a bit. So if you're looking from row to row to row, from lithium to sodium to potassium to rubidium to cesium, there you see that's the down trend. And then what we see here in this kind of trend here, that's the cross trend that goes that way. And then you see, some weird things happen when you get the transition metals involved. We're not going to worry too much about those right now. We're going to worry about mainly the main group elements for this class. But that's another way of looking at the data. Now, if you think about the ionic radius, there's less of a trend to talk about. You have a very hard time, say, comparing the size of ions from different places on the periodic table. But what we can do is we can compare the ions with the atom, and sometimes we could then make an argument about what the relative size are. So you got two types of ions. You either take away electrons, that's a cation. If you take away electrons, it's always going to be smaller, right? And the opposite of a cation is an anion. anion, you're always adding electrons, and that means it's going to always be larger than the atoms. So no question there. So here's two pieces of data here. You see that the aluminum +3 ion is not much more than half the size of the aluminum atom, and that the sulfur 2-, the sulfide ion, is quite a bit larger, not quite double, but still quite a bit larger than the sulfur atom. And remember that we say this is sulfide and this is sulfur atom, and sulfide is an ion. We'll be focusing more on those as we that language as we go on, but get used to that now. Now, a concept that is useful comparing the size of ions is the concepts of things being isoelectronic. Anytime you see iso something, that means something's the same, but something's different. Right? So isotopes, I-S-O-T-O-P-E-S, isotopes have the same number of protons, and they have a different number of neutrons, which means they have the same atomic number and a different mass number. So isoelectronic means that they have the same number of electrons, but they might have a different number of protons. So there are some examples here of isoelectronic species. You see that all of this first row has the neon configuration. All of this second row has the argon configuration of electrons. And basically then all you got to look at, if the electrons are the same, you just simply look at the number of protons. And the more protons you have, the smaller it is, right? So if I'm looking at this first isoelectronic series here, and I want to put them in order by size, N3- is going to be the largest. O2- is next, fluoride F- is next, then neon, then sodium, then magnesium, then aluminum, because nitrogen has 7 protons, oxygen has 8, fluorine has 9, neon has 10, sodium has 11, magnesium has 12, aluminum has 13. All of these have 10 electrons. So they're isoelectronic. That's the definition of isoelectronic. All right, ionization energy. Ionization energy is referring to the formation of a positive ion, and it's technically defined as something we measure in the gas state and removing that electron from the atom in its ground state, and the first electron removed is called the first ionization energy, or IE1, and we could go on and talk about the second and third and fourth and so on ionization energy for however many electrons we have on that. So ionization energy is IE. Now, if you think about how hard it's going to be to take away that electron, well, the further that electron is away from the atom, the easier it's going to be, right? So what happens is that if we think about our atomic radius, okay, this says that AR, atomic radius, increases, then the ionization energy decreases, because the further that outermost electron is, which is what determines the atomic radius, the easier it's going to be to take away. There are some deviations from it. Again, this is a general trend, but that's that. So here's some of the data that you look at this, and again, this is your atomic number, Z on the x-axis. You got your ionization energy here in kilojoules per mole. This is the first ionization energy. And what you see generally, let's look at lithium, sodium, potassium, rubidium, cesium. Kind of a slight downward trend there as you go down. And then as you go across any period, you see that there's an increase going across So the circles are the down period, and this line here is the across line, the period. So circles are down the group, and it decreases as you go down. As you go from left to right across a period, it increases. And so you can see those data. And again, you see, it's not a totally smooth curve. There are some bumps in the curve out there at different elements. And, later on you may have to explain some of those, but that's not going to happen in this course, or again, probably even the next course. Here are some actual values for the first ionization energies. And you could see here cesium's is the lowest pretty much, and helium is very uninterested in being ionized. Solar energy is one thing this applies to. The idea behind solar energy is you're taking light and you're using light to create an electrical current. To create an electrical current, you've got to get an electron away from a metal, just like in the photoelectric effect. Which metal would you choose? I would choose cesium if it was up to me, because that's the easiest one to ionize, to get that current going. Okay, so we'll just take a look at some of these last slides quickly. Again, I don't think we're going to go over this too much. We're probably going to defer most of this to Chapter 4, put some of this stuff together with Chapter 4. Again, the periodic table is organized by properties. We have metals, nonmetals, and metalloids. The main group elements are groups 1, 2, 13 through 18. The transition metals are the middle one, and the inner transition metals are the ones that are at the bottom. And we have names for some of the groups. You need to know those. Particularly these four: the alkali metal, the alkaline earth metals, the halogens, and the noble gases. So here you see those names in those areas. The main group elements are not these. The main group elements are these and these. That's what that's trying to represent, all of that area there. These are the transition metals, and then these are the inner transition metals, I think I called them. All right, so we're definitely going to defer compounds to the last unit for the course, and we'll talk about that then. So we're going to cut this video off at this point and look for some videos coming soon on going over the homework.